Hey everyone, it's Aniruth from CS61BL, and today we're going to be talking about the summer 2021 finals, specifically question 8B. So this question is dealing with multiple shortest paths trees and sort of expanding on what we did previously in the first part of this question. I'm going to go ahead and draw out what we sort of figured out, right? Our shortest paths tree was using AC, AB, BE, and then EF, and also using BD. So in that process, we had B was a distance of 1 away from A, E was a distance of 3 away from A, D was a distance of 2, C was a distance of 2, and F was a distance of 4. Now we want to see, are there any more shortest paths trees? So we know that there's one, but there could be others. So I'll go ahead and use a different color for this. Well, to B, it looks like this is going to be the shortest route, right? Because that's sort of like the point of Dijkstra's. There's no non-negative edges, which means that if every edge is non-zero, any route that I take using AC to get around is going to have more weight. So I know that there's nothing that I can do here. A similar line of reasoning goes for AC. By the time you get to E or D, you know that whatever you're going to do is going to end up adding more weight. So the part that really sticks out to me, though, is what we talked about before, which is that E has a distance of 3 away from A when we use AB and then BE. But we could get that same distance of 3 by using DE. In other words, I could have one tree that looks like sort of like this. Oh, sorry, without this part. And then I could have another tree that uses that part. So I have something more along the lines of this. Of course, these are not really drawn to scale. You have to sort of like imagine where the vertices are, but this is what like the two shortest paths trees would look like when you incorporate DE. The issue with incorporating something like CE or CF is that that would drastically alter the distance, right? So there would not be an actually valid shortest paths tree, even though it might be valid as just a regular sort of like path tree thing. For example, if I was to use CF to get to F, that would be a distance of 6, but then that's no longer a valid shortest paths tree because the actual shortest way to get there is 4. Now let's go down to number 2. We changed the weight of EF to 3. Well, the same reasoning from before applies about going AB, BE, and then also comparing that with going to BD and whether or not to include something like AB. Oh, well, actually, to go the other way around, right? To go like this. So we could have two different trees like this. But the question is, now that we've changed EF, do we have another way? And the answer is actually, yes, we do. So the big change that EF makes is the distance to F, right? So C, we're still going to be using a distance of 2, B will still be 1, D will still be 2, and E will still be 3. But the big change comes when, before we used to do EF, right? Well, now when we do EF, we still could, but the distance is now going to be 6. And the reason it's going to be 6 and not 4 is because EF was updated from 1 to 3. So in going through 6, the reason why I said earlier that we couldn't use CF was because if we use CF, the distance to F would be 6, which at that time was greater than if you used EF. But now that we've raised EF, it turns out that we can actually use either. So here is another completely valid path. So we basically have two different options. We have 2 options here, and we have 2 more options here, which gives us a total of 4 options. A quick note is that if I was to have like another set of 2 options somewhere, it would not be 6 total shortest paths trees, it would be 8 shortest paths trees. And the reason why is that these are kind of like independent of each other, right? If I choose this CF, right, that is independent of me choosing BE. So I have, for each combination here, right, I could choose CF or I could choose EF. I can also choose BE or I can choose BD, DE. And since there's no like conflict between the two, right? Like if I choose BE, that doesn't force me to choose EF or CF, that means I'm gonna have a total of 4. So I'm gonna go ahead and draw out the path structures that hopefully make a little bit more sense. So I can start out with what we had before, which is something along the lines of this. But now what we found out recently is we can use CF. So if I use CF, I'll have something that looks a little bit more like this. And then going along the lines of what we found in part 1 of this subproblem, I can also have one that looks something along the lines of this. And I can also then add in CF. So I could have something that looks more like this. And these would all be valid path structures. Now we want to come down to part 3, which is you want to change an edge weight to further increase the total number of SPTs rooted at A. Well, I think there's a couple ways to go about this, right? Well, we already sort of have one for CF and EF, which is that they are both balanced, right? In order to how we get to F. We have AB, BE, and then AB, BD, DE as a way to get to E. If we changed AB, right, that wouldn't really help us. If we changed AC, that also would not really help us, right? Because we don't really have like many ways to get to the other one. Maybe if I had something like B connected to C and then I had a weight of 1, that could give us more, but that's not even an option, right? We're not given that. So the place actually that I want to start with is CE. And you might say, why CE? Well, we aren't using CE right now. And the nice thing about having this sort of triangle structure, right, where you have multiple ways to get to something, is that maybe we could use CE to try to get to F or to E or something like that. So let's see what we could change CE to. The reason why we couldn't use CE was if I went AB and I went to BE, or if I went AB, BD, DE, I would always get to E within 3. But if I try CE, I would get to E with 5, right? Because AC is 2, then CE is another 3, so it'd be a total distance of 5, whereas I could get there in 3. So it's not really a valid shortest paths tree. So the difference is we're going to go ahead and update it. Instead of having 3 here, we can try a value of 1. And why 1 specifically? Well, because if I did a value of 1, then 2 plus 1 is 3. So now I'm going to go ahead and add in another valid mechanism to shortest paths tree. And so even though I can kind of, maybe I can like try, I can't really multiply by 2, right? I mentioned this before in the previous question about like how we found 4, but in this case, it's no longer independent, right? This new change. Because now if I draw the shortest paths tree, if I decide to get to E using ACE, well, then I can't use ABE or ABD. I would only be able to draw something like this. And then I have a choice as to whether or not I want to go like this or I want to go like this. So here we can sort of see that our answer would be CE, and we change it to 1. And the idea is now we have a way to get to E like this. We have a way to get to E like that. And we also have a way to get to E like that. So that goes ahead and wraps up this particular question.